Mars to the methane lakes of Saturn. Yet one planet seems to capture our imagination more than any other, the greatest of them all, Jupiter. Most of what we know about Jupiter comes from one space mission, Galileo, launched aboard the Space Shuttle Atlantis in 1989. Each new discovery it made deepened our understanding of Jupiter and its moons. It hoped to uncover evidence of how the solar system itself was formed. 11 times bigger than Earth, yet probably without a solid surface, Jupiter is a ball of gas and liquid 145,000 kilometers across, with lightning superbolts 1,000 times more powerful than the strongest strikes on Earth, and a ring system like Saturn's, but too faint for our telescopes to see. The Great Red Spot, a single vast storm with 250-mile-an-hour winds, so huge it could swallow the Earth 3 times over. 63 moons orbit this giant. Galileo set out to study 4 of them: Io, Europa, Ganymede, and Callisto.
Each of which would be a beautiful target for a space mission in and of itself.
Scientists expected dead and lifeless worlds 800 million kilometers from the Sun. Io, Jupiter's closest moon, is slightly larger than Earth's own moon, but Io is far from lifeless. Huge plumes of sulfur dioxide reach hundreds of kilometers into space.
Very peculiar surface with reds and yellows. Someone nicknamed it the pizza moon.
Ganymede, the largest moon, is a world of scars and frozen slush. And Europa, most mysterious of all, its icy surface may hide a liquid ocean below. And where there's water, there could be life. A new generation of probes is set to explore the mysteries of the Jovian system: Juno, Europa Explorer, and the underwater probe Endurance. 3 missions with one goal: to reveal the secrets of these alien worlds. Before Galileo, previous missions could only look from afar. In the 1970s and early 80s, Pioneer and Voyager gave us tantalizing glimpses of Jupiter and its moons, but they raised more questions than they answered. How did Jupiter form? What powers its vast storms? And why are its moons so geologically active? Before these questions could be answered, the team had to overcome a simple problem. Galileo was unable to carry enough fuel to reach its destination. NASA engineers needed another way to get to Jupiter.
And they came up with a brilliant solution. We wouldn't go to Jupiter at all. We'd start by going to Venus.
By flying close to Venus and then Earth, using a gravitational slingshot method, Galileo stole some energy from the planets to accelerate itself towards its final destination, Jupiter. When Galileo arrived, after a journey of 6 years, a small sub-probe was to detach and plunge into the depths of Jupiter's atmosphere. It would have less than an hour to analyze its surroundings before being crushed by the extreme pressure. Everyone expected Galileo to beam back extraordinary information. But first, it had to get there. Just 18 months after launch, disaster struck. Galileo's umbrella-like radio antenna failed to open.
It was beyond devastating. It had to open.
Without that antenna, we thought that the spacecraft would basically not be able to complete its mission.
Back on Earth, NASA engineers scrambled to fix the problem.
There were attempts to jolt it open. They thought perhaps it had just gotten stuck. There were attempts to, kind of go up and down, to try to get it to open.
There was now only one way to keep the mission from total failure. Use Galileo's secondary low-gain navigation antenna to send data back to Earth. But there was a big problem. The low-gain antenna transmitted 10,000 times slower. Just a few % of the data Galileo gathered would ever make it back to Earth. As the spacecraft neared the end of its journey, it coincided with a massive comet on a collision course with Jupiter. Galileo was in an ideal position to watch. It might be able to find clues to one of the most important questions about Jupiter's history. How was it made? Previously, scientists believed that Jupiter was made from the leftovers from the birth of the Sun, a primordial planet frozen in time. If this were so, then the Sun and Jupiter would have very similar chemical compositions. The comet's impact would stir up chemicals from below the surface, enabling the team to analyze them and see if the theory held true. They were about to get more than they bargained for.
I just couldn't believe that we were going to get a chance to see one body in the solar system smash into another one.
We had an up-close and personal view of this unique event.
The comet's name was Shoemaker-Levy 9. David Levy was part of the team that first discovered it.
This was going to be the first time that a comet collided with a planet, the first time in recorded history. And we had no idea what we were going to learn from it.
The day arrived. On mountaintops and in space, more telescopes were trained on the same part of the sky than ever before. As the comet approached, Jupiter's massive gravity tore it to pieces. 20 separate fragments would strike the planet, some more than 1.5 kilometers across. Astronomers across the globe were about to witness something amazing.
Yeah, that's it.
One by one, the fragments hit. The largest released as much energy as 300 million atomic bombs. A fireball shot 3,000 kilometers above the top of Jupiter's clouds. Each fragment produced a separate impact cloud, visible as dark black bruises in Jupiter's southern hemisphere. They were the size of the Earth.
The first thing we saw with each impact was either the plume of dust and gas as seen by either Galileo or the Hubble Space Telescope. The next thing we saw was the formation of the large jet black cloud all over Jupiter's southern hemisphere.
But the real surprise didn't come from the clouds. It came from the shock waves the impact sent through the upper atmosphere. There was only one explanation, and to astronomers, it was a revelation.
When Shoemaker-Levy 9 crashed into Jupiter, it's sort of like a rock going into a pool. It sent out waves, and the speed of the waves depends on the amount of water in the atmosphere. And the speed was faster than we thought, and so we inferred that there was more water than we had expected. You can sort of see it here. Well, you can see the ripples spreading out. And it was the speed at which the circles grew that told us there was more water than we expected.
The discovery was a surprise. It meant that the composition of Jupiter was different from that of the Sun. It threatened to overturn everything scientists thought they knew about Jupiter's formation. A new theory was needed. In 17 months, Galileo would arrive and analyze Jupiter's chemistry firsthand. Only then could the team hope to solve the mystery. 1 year after the comet Shoemaker-Levy 9 struck Jupiter, the probe Galileo was on its final approach. Evidence already collected had led scientists to believe Jupiter may have 10 times more water than previously thought. If so, they would need to find a whole new explanation for how this strange world formed. Galileo's first task would be to measure the chemistry of Jupiter's atmosphere, including the amount of water. Galileo would release a small probe into Jupiter's clouds. The probe would also measure the wind speeds and temperatures at different depths to try and explain why the weather is so violent, as well as answering the big question: is Jupiter a long-lost cousin of the Sun, or something else entirely? Mission Control fired 3 explosive bolts. The small probe disengaged from Galileo. Its goal was to penetrate the atmosphere of Jupiter. With the probe on its way, Galileo fired its engines, setting a new course to bring it into orbit around Jupiter. The images it took were thousands of times more detailed than any taken before. Then, 2 months out, there was a disaster. The tape deck used to record the vital data jammed.
What they discovered was that this tape recorder, if it was run at very high speed, was prone to the tape actually getting hot and sticking.
And so we re-engineered the mission so that we would only use the slow speeds of the tape recorder, and we didn't use the whole thing. So that, coupled with the antenna, really limited the amount of data and how fast we could send the data back to the Earth.
The malfunctioning tape deck was a bitter blow. 5 months had elapsed since Galileo launched its probe. Soon it would plunge into Jupiter's atmosphere to measure its water and other elements. After the impact with the comet Shoemaker-Levy 9, scientists were left with fundamental questions about how Jupiter and the planets formed. Could this tiny probe give them the answer they had been waiting for? The small probe needed to enter Jupiter's atmosphere at precisely the right angle. Too steep and it would burn up. Too shallow and it would be thrown off course.
Everything was calculated to just go in at just the right angle, and it had a big heat shield that was protecting it. Very tense moments as this probe went in.
2 minutes of aerodynamic braking slowed the probe to the speed of sound. A drogue parachute was deployed. Then, silence.
There's a period when a probe goes in where you can't receive radio signals from the probe because of the tremendous heat that's being generated as the probe hits the atmosphere.
As the probe slowly descended through 200 kilometers of atmosphere, it collected the data and relayed it back to Galileo and then to Earth.
And it's trying to measure all the components that are going into Jupiter. What is it made out of? Sulfur. What are the noble gases? The neon, the argon, the krypton. How much is there? How much water is there?
As the probe dived into Jupiter's atmosphere, scientists were convinced they would find the layer of water vapor the comet had revealed, giving vital clues to the planet's creation.
And I even announced a prediction at a scientific meeting, offering to bet anyone in the audience $10 that the probe would find more than a certain amount of water.
But instead of water, the probe drifted through thin, wispy gases. It had flown into a downdraft, a dry gap in the clouds. Where was the water they had expected to find? Jupiter must have both dry areas and wet spots.
What they discovered was that Jupiter has some long-term weather patterns, spots that move around that they didn't really realize were there before.
The probe went deeper still, but there was almost no evidence of water. Less than an hour's worth of data was about to trigger a revolution in our understanding of how the solar system formed. The probe detected a high proportion of heavier elements like argon, krypton, carbon, and nitrogen. It found levels 2 to 3 times higher than found in the Sun. These elements only condense at extremely low temperatures, lower than the temperature found at Jupiter's present position.
We learned that the atmosphere of Jupiter has chemical constituents that came in with very cold material from the outer solar system.
For astronomers, the discovery was a bombshell. The presence of these elements meant Jupiter must have formed in a different way from the Sun.
This little probe, in one felt swoop, showed us that all of our ideas of how planets were formed were wrong. We didn't understand how the planets were made, and we didn't understand the early solar system.
The small probe's discoveries shocked the scientific community. Could the giant planet have formed further out in the solar system where it's colder, then migrated into its current position? Or did comets or asteroids bring the heavy elements and water to it? After 58 minutes, and before the answers became clear, the probe fell silent, burning up in Jupiter's inner atmosphere. The probe had given scientists some remarkable insights into Jupiter, its atmosphere, and how it formed. But questions remained. In 2011, a new mission, Juno, will attempt to find answers, closer to Jupiter, and gather more information than ever before.
What we're really after with Juno is the ingredients. From the ingredients of Jupiter, we're going to figure out the recipe. And that's what's going to tell us how planets are made.
With the probe having completed its work, it was now time for Galileo, 200,000 kilometers above Jupiter, to turn its attention to another long-standing mystery, the planet's weather. How can storms 3 times the size of Earth get so big and last for over 300 years? Jupiter's weather is a maelstrom of swirling clouds, lightning storms, and massive hurricane-like vortices. For the Galileo team, it was a mystery. On Earth, weather like this is powered by the heat of the sun, but Jupiter is 800 million kilometers away, so there must be some other source of power. Its most famous feature is the Great Red Spot, a storm whose clouds tower over 8 kilometers above the atmosphere and plunge deep into a chemical soup below.
The red spot is red because of the chemicals that are trapped there in the center of the red spot have been baked and cooked by ultraviolet light and have turned red.
Astronomers have watched the Great Red Spot for at least 300 years. On Earth, even the biggest storms only last about 2 weeks. So how does the biggest storm in the solar system, 3 times wider than the Earth, get enough energy to rage unchecked for centuries? Scientists believed smaller thunderstorms could hold the answer. In order to solve the mystery, they had planned to video the Great Red Spot and other smaller storms in action. The Galileo team hoped that understanding the mechanics of these turbulent weather systems would reveal the source of their power. With the high-gain antenna out of action, this simple solution wouldn't be possible. The team back at Mission Control needed a new approach.
Instead of making long, continuous movies, we made 3-step movies. You watch the red spot, you come back a few hours later, you watch it again, and so it's just a 3-step movie instead of a continuous movie.
Galileo homed in on a turbulent area of small white spots, which scientists believed were caused by convection or rapidly rising air. If these were storms, they would need to find proof. They needed to locate another of Jupiter's most extraordinary features: lightning bolts 1,000 times more powerful than on Earth. But these are only visible at night.
Jupiter is 11 times bigger than the Earth. It's really big. If you look at this globe, you can see a few intense white-colored spots, small, intense white-colored spots. And when we got around behind Jupiter and looked at the night side, it was those very white-colored spots that had the lightning in them, and no place else. So that identified where the thunderstorms were.
Having identified the thunderstorms, the next step was to find out whether these small white spots can grow into larger ones. Galileo was in the right position at the right time.
There were some white ovals that formed in the 1930s, 3 of them, and they had been around for 60 years when suddenly 2 of them merged.
Galileo watched as 2 of the ovals merged to form a larger, more powerful storm. 2 years later, the 3rd oval also merged, forming one large storm in a belt below the Great Red Spot.
And then it had slowly turned red, so that it resembled the Great Red Spot, but not quite as big.
Nicknamed the Red Spot Junior, it was hoped that observations of its birth might also help to solve the mystery of where these large storms get their energy. Jupiter's larger storms swallow smaller storms. This is how something as large as the Great Red Spot came into being.
It's like a food chain where the big fish eat the little fish and the little fish eat smaller fish. And the primary harvesters of energy on Jupiter are the little thunderstorms.
This accounted for the source of all the energy, but it didn't explain why these vast storms last for so long. Conditions on Jupiter are so turbulent that the storms should blow themselves apart. On Earth, vortices such as tornadoes soon die out, but on Jupiter, vortices last for years. It is the fastest spinning planet in the solar system, turning 22 times faster than Earth. Scientist John Arnaud thinks this rapid spin explains the stability of Jupiter's storms.
In rapidly rotating systems, vortices can be long-lived. It's very surprising. Normally we would think they'd shred themselves. They never do. What we've learned from these missions is that it's very coherent, is that it's very stable.
When 2 different colored dyes are mixed in a rotating jar of water, the results are startling.
At first, what looks like it's going to be a mess quickly turns out not to be a mess. Instead, we generate 2 large-scale vortices that you'll see are going to be very long-lived and coherent. And this is the idea. In rotating fluid systems, when you try to mix them, instead of just destroying any dye signal or any signal in the fluid, you get large-scale structures, similar to a Great Red Spot.
Galileo revealed why some storms get so big and last so long. But scientists are still mystified by Jupiter's most distinguishable characteristic, its red, white, and brown stripes. It was assumed that some colors are rising gases and others sinking, but Galileo found this may not be true. Although its atmosphere is hundreds of kilometers deep, only the surface layer is visible. Here, high-velocity winds blow in opposite directions, causing these multicolored patterns to be dragged across the surface.
The colored bands are associated with vertical motion, and some of them are mapping out rising motion and some of them mapping out sinking motion. It may be that the rising motion happens at one level and the sinking motion happens at the same bands, but at a different level.
Scientists will have to wait until the Juno mission in 2011 to look through the top layer of Jupiter's atmosphere and see just how the planet is spinning. The 2011 Juno mission will orbit Jupiter 32 times, each orbit lasting 11 days. The orbits will pass over Jupiter's north and south poles, shifting longitude with every flyby to scan a new section of the planet. For the first time, Juno will map Jupiter's entire atmosphere down to a depth of more than 550 kilometers. Jupiter's vast weather systems may finally yield their secrets. Scientists now realize that the planet's fast rotation maintains Jupiter's long-lived storms, but more importantly, it also drives Jupiter's most powerful force, its magnetic field.
And we can study that system and compare it with what goes on at Earth and learn a lot that will help us understand Earth as well.
The Earth's magnetic field is generated by the churning motion of molten iron around the core. Jupiter is made of gas, but at its core, the hydrogen is so compressed it acts like liquid metal.
The magnetic field is created deep down in the planet where the pressures are so great that the hydrogen in Jupiter has become metallic. It actually behaves like a metal. And so it's moving around and currents are being created. And these manifest themselves out into the magnetic field that surrounds the planet.
The metallic hydrogen churning in Jupiter's core creates an incredibly powerful magnetic field around the planet. It stretches across the solar system to Saturn and beyond, holding in its grasp charged particles and gases.
It's enormous, 50 to 100 times Jupiter's size and going across, and the tail is dragged out by the solar wind all the way back to Saturn's orbit.
Jupiter's magnetic field is massive. If it could be seen from the Earth with the naked eye, it would appear larger than our moon. It's also strong enough to divert the constant stream of sulfur emitted from the huge volcanoes on Jupiter's closest moon, Io. This material also funnels down towards Jupiter's poles, creating a breathtaking light display. Like Earth, Jupiter has northern and southern lights called aurora. For the first time, Juno will analyze the charged particles and magnetic fields that create these huge displays.
We're flying close. We'll dive underneath the radiation belts and out the other side. And we'll fly through the charged particles that bombard and light up the atmosphere with the northern aurora.
The team hopes the study of Jupiter will yield a better understanding of the dynamic processes that create Earth's own magnetic field. But the Jovian system has other secrets to offer. Its moons are not cold and inactive, but dynamic worlds that may hold the answer to the ultimate question: is there life beyond Earth? The Jovian system is immense. 63 moons orbit the planet, some large enough to be planets in their own right. They're also an enigma. Small planets and moons usually cool faster. So how can these moons be so hot and geologically active now? The answer may contain a clue to the holy grail of science. Is there life on other worlds? The four largest moons are Ganymede, Callisto, Io, and Europa. Each one is profoundly different.
Where every time Ganymede goes around once, Europa goes around twice, and Io goes around 4 times. It's not a coincidence. These moons have evolved into this wonderful cosmic dance.
Astronomers had expected Jupiter's moons to be cold, dead lumps of rock and ice. What Galileo found were active, dynamic worlds. First stop was the mysterious Ganymede, the largest moon in the solar system. If it orbited the Sun instead of Jupiter, astronomers would call it a planet. These NASA images show its mountains, valleys, craters, and frozen lava flows. Almost immediately, the team found something extraordinary. Galileo's magnetometer was picking up unexpected readings.
I was flabbergasted. The evidence right there that there was a magnetic field caused me to say, I don't believe it.
Ganymede is the only moon in the solar system with its own magnetic field, but it's a puzzle. The moon should be frozen solid. If Ganymede's got a magnetic field, it must have a molten core. The discovery of Ganymede's magnetic field only deepened the mystery of how planets form. Something must have happened in Ganymede's past, something catastrophic enough to have heated up this moon.
Galileo showed us that Ganymede is a fascinating world, one that's gone through a very complex history, a world in its own right.
But as well as detecting Ganymede's normal magnetic field, Galileo found a second varying field.
That's telling us there's probably also a liquid water ocean within Ganymede.
Scientists suspected this ocean was buried deep beneath the moon's rocky crust. The team was eager to investigate, but Galileo's orbit meant it had to leave Ganymede and move on. More surprises lay ahead. Next was the outermost of Jupiter's 4 largest moons, Callisto, cold and rocky. The oldest and most heavily cratered landscape in the solar system, its surface is scarred with ancient meteorite impacts. Scientists were perplexed by craters with strange bright rims. It seemed dark surface material had slipped away, exposing the lighter material below. Nothing like it has ever been seen on Earth.
So what's the material made of that's slumping down? What's the process that's causing it to slump off? And it certainly proved to be a much more interesting body upon close examination than we ever thought.
Although the surface is minus 170 degrees Celsius, Galileo's data suggested that just like Ganymede, Callisto can't be frozen solid. It detected a very weak magnetic field suggesting it too may have an ocean. But the data was confusing. Other instruments aboard Galileo suggested that 200 kilometers beneath its surface, Callisto consists of a mixture of rock, metal, and ice right down to its core. It was another mystery. The standard theory of how moons and planets form says that they should heat up when the material they're made of first joins together. The heat should then separate the rock from the ice. Strangely, on Callisto, it hasn't.
That would mean it never got really hot in there. How do you make such a large moon and not have it heat up? We still don't really understand Callisto.
Like so much of the Jovian system, Callisto raises more questions than it answers. We don't know what's going on inside the moon. We don't even know what material covers its surface. The story of Jupiter's next moon is equally bizarre. Io is the same size as our moon and is the closest of Jupiter's 4 large moons. It's the most volcanically active body in the solar system, with over 400 volcanoes, up to 200 kilometers across.
If you could have a bird's eye view of Io, it would be really extraordinary. You would see these plumes that are hundreds of miles high, these enormous lava flows, and big lava lakes just boiling and bubbling away on the surface that is all really strange and has these colors of pepperoni pizza.
Volcanoes constantly reshape Io's surface. Galileo's pictures were totally different from the ones Voyager had sent back some 20 years before. But how can a landscape change so dramatically in such a short space of time? Huge craters seem to come and go. The cause of their disappearance seems to be giant plumes of sulfur-rich gases shooting around 320 kilometers above the surface.
We concluded that it was the plumes that were depositing fine material on the surface and actually erasing these craters over long periods of time.
But as with Jupiter's other moons, there was a further mystery. This much volcanic activity requires an immense amount of heat. But where had it come from? Io, 800 million kilometers from the Sun, should be too cold, but clearly it wasn't. Could the answer be gravity? Jupiter's gravitational field keeps Io in orbit, but as it goes around, it passes on the inside of Jupiter's other moons. Their gravity pulls Io in the opposite direction. That distorts Io's shape. It's the distortion that creates the heat.
As Jupiter's large moons orbit around the planet, they're pulled and pushed and squeezed as they go around in their orbits. And this creates heat, friction, and causes melting within Io of the rock to power its volcanoes.
It raises tides on Io, very much like the moon raises tides on the oceans on Earth. Only on Io, the whole surface goes up by over 300 feet. Can you imagine what it would be like on Earth, like here in Los Angeles, if the crust of the Earth was rising 300 feet?
It was an astonishing discovery. A world pulled apart, shaped by violent forces. Yet, as amazing as it sounds, of all Jupiter's moons, Io may not be the strangest. The next moon on Galileo's path was Europa. Its surface is covered in strange geological shapes and parallel tracks that cut across the ice. It's an ice world with an extraordinary secret. Could it harbor the ingredients for life? Images of Europa from earlier missions reveal a pinkish-white world. But Galileo found fewer meteor craters than expected. That meant something was erasing the craters after they formed. Because Europa's surface is ice, scientists believed water could be welling up from below. This moon was so intriguing, the team wanted a better look. But to do so would mean spending more time at Europa than planned.
The original schedule called for only 3 flybys of the moon Europa, but the evidence was so compelling that it compelled the mission to be extended in length and to go back several more times.
Galileo's first job was to image the moon in greater detail. The question was, how active is Europa's surface? Are the processes that erase impact craters fast or glacially slow? The team began by assuming the process could take billions of years. That assumption changed fast.
I'm listening to them discussing the age of Europa's surface dropping. Oh, well, maybe it's a couple billion years old. And then the next flyby, well, it might even be 100,000 years old. And then the next flyby, it may be currently active.
While measuring Europa's magnetic field, Galileo uncovered another mystery. As the moon orbits Jupiter, its magnetic field shifts. Europa must have a conductive layer which allows Jupiter's magnetic field to pass through it. There is only one thing that could have caused this, and it was a big surprise for the Galileo team.
We were able to interpret these signatures as being produced by a global ocean beneath the surface of the ice.
Scientists believed Europa's ocean was vast, covering the whole globe to a depth of 160 kilometers, making it the largest body of liquid water in the solar system. If this was the case, the team would first have to address a fundamental problem. Europa's surface temperature can reach -93 degrees Celsius. Why doesn't such a huge ocean so far from the sun freeze? Astronomers thought the answer to this question might be the same one that drives the volcanoes on Io. Jupiter's gravity stretches and compresses the moon, creating heat within. It's the heat that keeps the surface in constant motion. This could also explain some unusual features found on Europa.
Galileo images showed that ridges crisscross the surface of Europa. These are bizarre features that travel across the surface for up to 1,000 kilometers, and typically in pairs. That is, a ridge with a depression in the middle and another ridge. These are bizarre features like nothing we see on the Earth.
At first, these ridges were a puzzle, but researchers soon came up with a solution. Planetary scientist Bob Pappalardo reproduces the effect with ice blocks in the lab.
As Europa is flexed by Jupiter's gravity, its surface bends and cracks and makes fractures through the ice. Well, as it's squeezed and bent, the ice slides back and forth along these fractures. Now, this can create heat as these blocks move by one another. And that heat can warm the ice on either side of the block, and that warm ice rises up to form these strange ridges that we see, these tracks that seem to go across the tundra of Europa.
Galileo revealed a world in constant motion, evidence of heat hidden below the ice. Flows of material on the surface are possible evidence of ice volcanoes or geysers. Brown-red stains stretch across the ice, where it's cracked open, and salty material from the interior has welled up from below.
We see pits and spots and domes on the surface of Europa that might be related to the rise of blobs of warm ice that move up through the shell, sort of like a lava lamp.
Heat from the interior of the moon may even drive hydrothermal vents in the ocean. On Earth, hydrothermal vents on the sea floor are hotspots for life. Galileo's data also suggested there's carbon dioxide frozen on Europa's surface, possibly welling up from the ocean below. If so, the find was huge, because carbon dioxide is vital for life. Does this mean there's life on Europa?
I'm in the camp that where there's water, there's a very good chance that there's life, and where there's materials for that life to use. And on Europa, we seem to have the materials and we have the water.
If we search and find life within the ocean of Europa, that'll be an enormous leap in understanding whether we're alone in the universe or whether life may be everywhere.
The search for life is an irresistible lure. Scientists are desperate to go back to Europa. Near the end of the next decade, they hope to launch a groundbreaking mission to orbit the moon. The Europa Explorer will take the first steps towards answering the biggest question of all: is there life on other worlds? It will survey the ice on Europa's surface. As well as analyzing its structure, it will search for spots where we could one day break through to the ocean beneath. The Explorer's main tool is radar. It will give scientists a three-dimensional map of Europa's crust. This will tell them just how thick the icy shell is.
How far beneath the surface the ocean is, if it's a global ocean, how deep it is, how thick the ocean layer is.
These are crucial questions. Once scientists know how thick the ice is, the next step is to work out how to get beneath it, and that will mean a completely new mission. A probe that will not only orbit Europa, but land and explore its subsurface ocean. A robotic submarine, Endurance, is already at work in Antarctica. It's the first of a new breed of underwater probes that can also operate under the ice. The aim is to create a vehicle that needs no instructions from home. Endurance must make decisions all by itself. Perhaps one day a vehicle like this will search for life on Europa. But first, it has to get through the ice.
That thick ice cover, it takes a lot of energy to melt ice. People don't usually appreciate that, but we'll need some kind of nuclear system that will melt that ice, and it will take weeks, perhaps months, to get through that ice.
We might imagine a lander spacecraft that melts its way all the way down to the ocean and explores what's really down there.
The discovery of life on another world would be one of the greatest finds of all time.
If life exists in the ocean of Europa, that would tell us that life probably exists almost anywhere there's a water-rich environment. That would be an amazing discovery.
Jupiter and its moons have already transformed our understanding of our place in the solar system. Now, new missions to Europa may finally prove that life on Earth is not unique. and if there's life on two